If I can teach physics 2, I'll try to. Mainly because I think it'd be cool to follow you all along to the next class. But that's so much of that is out of my hands. It'll for all sorts of reasons. All right, y'all. Well, howdy. Good early evening / late afternoon. We're gonna finish up oscillators today. It'll be a good time. So recap on last class. Last class, Friday we did gravity. I already did the recap on that, so I'm not going to do that again. Last class we talked about things that wiggle back and forth. That was kind of the entire class last time. We did also connect gravity to things going in a circle. So, okay, I will mention that. If it's going in a circle, orbiting, all that jazz, you set the equation for gravity equal to mv squared over r. But the majority of our time was looking at this thing. Up and down, or left and right, pick your poison. It does the same thing whether it's up, down. It oscillates, it wiggles, back and forth. We talked about frequency. Frequency is how many times it completes a full cycle per second. Frequency is how many times it completes a full cycle per second. So, in this case here, we would, in 1 second, how much of a cycle does it do, or how many cycles, could be a fraction, whatever. So a cycle here is not down, a cycle here is not up, it's down and then up. It's a full thing. So pick some spot, a full cycle is when it returns that spot. That could be bottom to bottom, that could be middle and then going back to the middle, whatever, maybe. Frequency was how many cycles per second. We then introduced period, which is the inverse of that. So instead of cycles per second, flip that. Seconds per cycle. That's where the math comes from. F equals 1 over t. And then I really tried to hammer this, and I'm going to keep really trying to hammer this. We had something called angular frequency, omega. And this is the radians per second. How many radians I complete per second. Not the same as frequency. Very similar, but they are not the exact same thing. Conversion is super simple. Just multiply frequency times 2 pi, AIE, the radians in a circle, and you get that. Yeah?
So frequency is just revolution?
Revolution. If it's going in a circle, it'll be revolutions. If it's wiggling back and forth, it would be oscillations. If it's whatever that repetitive motion is. Take whatever one full thing. So if it's going in a circle, that's one full. How many revolutions per second?
You're saying, like, let's say the angular frequency was actually just like pi. I mean, I don't know. What I'm trying to say is, like, let's say the oscillation isn't like a full circle.
Sure. So if it doesn't make a full, say it wiggles back and forth between, makes a half a circle or something like that, it'd be how much time does it take to repeat itself? How many times does it repeat itself per second? That's what frequency is. How many times does it repeat itself every second? Whatever that pattern may be. And then angular frequency, we specifically think of something kind of going in a circle, generally. And it's number of radians per second. There's 2 pi radians in one thing, so yeah, kind of. So like even in this picture, you're like, there's no angle here though. Yeah, but the function ends up being a sine wave. So yeah, so angular frequency is just radians per second. Frequency is events per second. The conversion, just multiply frequency times 2 pi. And as we kind of solve more and more of these, we'll see real examples, I guess, of frequency versus angular frequency. So that may help. We're going to eventually learn that angular frequency is also called angular velocity. And they're the same thing, and they have 2 different names, and that's weird. How many angles per second? That's angular velocity. But that's a future thing, i.e. after the first test or the second test. All right. Amplitude, that was the easiest one. How much maximum displacement from equilibrium? We said this is a sine or a cosine wave. How do you choose? I'll tell you. I'll tell you which one it is. We'll go ahead and use like cosine. And then I wrote in all caps, make sure your calculator is in radians mode, because when you plug this stuff in, omega t ends up coming out as radians, because omega is radians per second, t is seconds, seconds cancel, you get radians. If you try plugging this in degrees mode, you will not get the right answer. It will be very sad for you. I will not... Oh, I'm pretty sure I wasn't mean. So like, if a question like this shows up in the test, I'm fairly confident I wasn't mean, and if the answer for doing correctly, is one of the choices, I don't believe I put another one of the choices as if your calculator was in degrees mode. So if your calculator is in degrees mode, you shouldn't get an answer that pops up there at all. It's kind of a flag if something's wrong. Okay, yeah?
I'm more curious, after that scene, this is kind of like a universal thing. Why is it that like part of this class uses degrees if like radians is required for a different word?
Sure. Yeah, so it comes to discussion why radians sometimes, why degrees other times. To be honest, it's just because this is one of those things that people aren't consistent on. It's very often across all the disciplines that people describe angles as degrees because they're comfortable with it. It's not very often you'll get a problem where it'll say I have a velocity vector pi over 6 radians above the x-axis. It just doesn't, people just don't like, we like degrees because they're easier to like pi over 6 sounds just like really weird, whereas like 30 degrees, it's easier to visualize. So like we use degrees when we're visualizing angles because it's easier, but then when we do stuff like this, we have to use radians. So I guess that's the reason. I guess it's like a psychological, social reason. Our brains, and maybe if we only use radians, our brains would get really good at it. But degrees, since upbringing, like people have seen degrees years and years and years, so we tend to use those whenever an angle is given in like a picture. Because it's easier understood, and then stuff like this, we have to use radians. We're just kind of forced into it. It's a good question. It's an interesting question. So yeah, you can either use cosine or sine. They're just shifted, but remember this thing repeats itself again and again and again, so it ends up being the same. I will tell you which one to use. I will tell you if there's a test, and I say, write the function for an oscillator with amplitude this and frequency this. I will say, write it as cosine, or I'll say, write it as sine. I'm not, or every single answer will be in cosine, and you won't have to guess, because technically both are correct. So, all right. So then we did a couple examples of that. Specifically, I gave you the function, and I said find the angular frequency, and this was basically to see, again, that there's that distinction. So this is the function for it, x equals a cosine omega t. This is the form, meaning the angular frequency was just the 3 hertz. Whereas when I asked you for frequency is not the 3. Omega, angular frequency is the 3. To convert it, you just divide it by 2 pi. Okay? And that's where we ended last time. So things oscillate, they're described by a cosine function. Frequency and angular frequency aren't the same thing. There you go. That's the recap from last time. Okay, this should be easy. This is the last one. We didn't have time for it, but it's the easiest one. What is the amplitude of the following function? Is it 3 hertz? 3 over 2 pi hertz? 5 hertz or 5 meters? You can guarantee on the test, I will have, and I got some questions about this during the last test, and they're reasonable questions. The questions were, did you mean to put this unit as one of the answers? Yes. I will totally give you multiple choice answers with different units on it. If you know the right units to use, that actually is a benefit to you, because you automatically can rule out if it's the wrong unit, who cares what the number is. Units are very, very important. It is the language. If you don't know the units, it's kind of like not knowing the right word in the language. It's like calling something a cat, that's a dog. So, anywho, All right, we'll go to 1 minute. This is fairly straightforward. I am loving that I'm tricking people. This is not a trick question. So I say trick. I'm loving that I'm seeing different answers. It means there's a good question to ask. All right, 5, 4, 3, 2, 1. And then so you heard my statement. It's like, why am I happy to see? So let me just go ahead and show you what I saw. If everyone gets a question right, then basically, what was the point of if everyone knows how to do it, that's good information for me. But when everyone doesn't know how to, or when there's some people that don't, that's a really good thing for me, because then I can, oh, hey, let's point out this thing real quick. So yeah, the answer here, y'all, is 5 meters. If you put 5 hertz, this is just a good reminder. Fun fact, if you make a mistake, you're more likely to remember it than if you get it right. Anyway, so sometimes making mistakes is a good thing. It's best to make mistakes now versus later. But yeah, so this is the amplitude, so it's the same function, x of t equals a cosine omega t. The amplitude is 5. It's x of t, the units are meters, according to this function. So just reading the function. Amplitude will never, if the amplitude was also in hertz, it's technically possible if you had a function of frequency with respect to time, and that frequency oscillated with respect to, and then that gets kind of funky because you have a frequency of a frequency, which is possible. You know, a frequency of anything, but yeah, the units come from the end. Meters. All right, so now we're just going to kind of a couple problems, and then I'm going to give some very specific scenarios and some equations for those. So reciprocating motion. So reciprocating motion is where you take something that is going circular and you convert it to linear. Very, very useful. Very, very useful. There's all sorts of situations. Like a saw is one. Almost every single motor starts with circular motion. Almost every single motor that exists starts with circular motion, but not every useful application is circular. Like in the case of a saw, you don't want your saw, I guess you can spin a saw blade, that's one way. But if you have like a jigsaw, I think that's what those things are called, where the thing goes back and forth. Depending on your function, sometimes you want linear motion. So how do you convert it? This is kind of the diagram for it. So if the motor rotates at 60 hertz and has a radius of 3 centimeters, estimate the maximum speed of the saw blade as it moves left and right. All right. And it's got a fun name. I didn't know the name. It's Scotch yoke. If you had asked me what this is called, I wouldn't have known that. But fun fact, it's got a name. All right. So let's think through this. Let's write down our givens. We have if they don't clarify, if they don't say angular frequency, we can assume that this is normal frequency. If it doesn't clarify, you can assume it's normal frequency. We have a radius of 3 centimeters, which comes out to 0.03 meters. Always good to convert. And we are trying to find the maximum velocity, Vmax. All right, there's a few ways we can kind of do this. I'm going to go with the math way. You can kind of logic through this. Yeah, I mean, it kind of makes sense. The faster the thing spins, the more that blade's going to wiggle. But what is the way I recommend doing this? Well, we have something oscillating, so we can write the equation for its position with respect to time. And whatever is happening here, this thing is following the same idea. When this thing on the bottom moves to the right, the saw blade moves to the right. When the circle is moving to the left, when this piece here is moving this way, the saw blade moves that way. At the top, when it moves to the left, the saw blade will move to the left. So whatever function that we make for this oscillator is going to be the function for this. I want you all to see if you can, I'm going to go ahead and tell you it's the equation for an oscillator. In fact, here's the form of it. A cosine of omega t. I want you all to see if you can plug in the values. And you may be like, why are we doing this? It doesn't say anything about position. Also think through why I'm writing this down. See if you can logic through that. Yeah.
Wouldn't it be the side of the circle, not the top? When it starts moving to the left.
Oh, yeah. I mean, it's moved, but I just picked an arbitrary spot. At the top, it's moving to the left. At every spot up here, it's moving to the left. Yeah, you are correct. At every spot here, it's moving to the left. I just picked a random spot. All right, so see if you all can plug the things in, see if you can make the function. And then also, once you do that, or if you're still either way, I also want you to think about how the heck is this going to give us velocity? See if you can figure out what next step I will do after that. So the amplitude is going to be the maximum displacement. So if you think about it, this is my equilibrium. This is like my equilibrium position. However much it moves away from that, that's my maximum displacement. So my amplitude is going to be 0.03. It's the radius. That's the max amount it moves one way or the other. It doesn't matter. That's the max amount it moves. It moves 0.3 meters this way, or 0.03 meters that way, and moves 0.03 meters that way. And then cosine, and we have to do the 2 pi ft. Could have put the numbers in, but I wanted to show you all that before I put the numbers in. Remember, omega is 2 pi f. We're given f, not omega. How do we know that? If you ever say something rotates at this thing, that's the number of rotations per second. 60 hertz is the rotations per second, i.e. events per second, i.e. frequency. Okay, so x of t equals 0.03 times cosine of 60 times, we'll just put 120 pi t. It's a number, some number. Is it 377, some decimal after it, right?
It's 376.99.
Sure. We'll put that. Okay. And now, if you haven't already thought about it, I'll give you 5 seconds. How are we going to get velocity from a position function? So throwback to kinematics, y'all. Yeah, we're going to, derive it. Derivative. Derivative of position with respect to time is velocity. The definition of velocity is dx dt. So, derivative of cosine is going to be negative the inside, so 376.99 times 0.03 times sine of the original inside. 376.99 t. Now, the problem didn't ask us to find the equation for velocity. It was actually, we need this for the next step. What we need is the max velocity. So the trick to that, there's only one thing that varies here. It's my sine function. And the cool thing is, I didn't say at what time is my velocity maximum, because honestly that's not quite clear for this problem. You couldn't actually find that. Again, we could have chosen sine or cosine, you get different answers either way. But what matters, what's the maximum value that sine can be? It's 1, yeah. So basically, Vmax is just the amplitude, the amplitude of this function is Vmax. So Vmax just equals negative or positive. It says maximum speed. So, you know what? I should have been a better, not 0. Magnitude of velocity, i.e. we don't care about the positive or negative. It just says maximum speed. So absolute value of velocity. Yeah.
The negative 376.
Oh, derivative cosine is negative sine. Yeah, it's a good question. Yeah, to clarify this negative cosine, you take the derivative, you get negative. Doesn't even matter. Doesn't even matter for this problem. Because Vmax is just 376.99 times 0.03. It wants the average, it wants the speed, which is the absolute value, which negatives go away. So you just multiply those two numbers, it gives you an answer. And that's the maximum velocity. That's it. So this problem that seemed really weird, probably at first glance, like how do you begin to solve this? Equation for an oscillator, do the derivative. 11.31 meters per second. And remember, y'all, there's always one last step. Is that reasonable? 20. So the conversion, actually, this is more useful. If you multiply meters per second times 2.2, you get miles per hour. So multiply this by about 2, you get about 2.2, 23 miles per hour. That's reasonable. It's fast. Like, these stalls go really fast, but not like, it's fast enough that if something's traveling 23 miles per hour and it's got sharp points on it, it's going to cut stuff. But not so fast that you're just like, that's too fast. So, cool stuff. There you go. All right. So there you go. That's an example of a problem where you'd use the function for it. And what's cool, again, all this is like real world. Like, yeah, how fast it rotates, the radius of it, all that jazz. Yeah. Oh, that's a good question. So we said, when is it maximum? So for it to be maximum, this term, we pick when is sine maximum. And sine is maximum when it equals 1. So what's the maximum value that sine of anything can be? Is 1. So that is such a good question that I'm going to go ahead and make certain I clarify that on here. Just so that when you are looking at this later, or anyone who may look at this later, can also remember why. Because it looks like I just skipped a step. It looks like I just chucked it in the trash, which, on some level I did. But there's a reason why I chucked it in the trash. Okay, so max is maximum of sine equals 1. There we go. So that'll be in there if you ever look at this later and wonder where it went. If I wanted the average, a few ways I could do that. Find the velocity at the lowest point, find that, divide it by the time, or you could integrate it. But I'm not asking for that, so we don't need to worry about it. All right. Okay. Yeah. What's up?
If you ask for the minimum, you just make it negative 1.
What's the minimum a sine can be? I guess that's technically a minimum.
Or 0.
0 would be the one we'd pick, because if we did negative, then it just goes the other way. So that wouldn't give us the minimum speed. It would give you actually the maximum speed in the other direction. The minimum speed would be 0. So when the linkage is right here, it's not pushing it in any direction.
Yeah.
So that thing comes to rest. Yeah. Yeah.
So math-wise, are we doing it so that sine is like sine equals -1, or are we doing it so that it's the absolute value of the velocity?
We're doing absolute value velocity. Yeah, because it said for maximum speed, speed is going to be a positive number. Yep. So if you've gotten your maximum velocity as negative 11.31, then you just be like, oh, absolute value, I want positive. Because I don't care which way this saw is going, left or right, I just care how fast it's going. That speed is sometimes very useful, sometimes we don't need direction, and this is that case. Yeah, these are all great questions. Okay, so the next slide I'm going to show you, I've already kind of mentioned to you, but there's going to be a reason why. So the energy in a simple harmonic oscillator, because that's, we're talking about things that oscillate. It's just the energy in a spring. I mean, if we looked at our original problem, so let's go ahead and take that thing that's been bouncing up and down on a bunch of these slides. If I said, hey, how much energy does this oscillator have? It's a spring, y'all. We've already talked about the energy of a spring. It's 1/2 kx squared. It's not new. So that's nice. If you're like, whoa, what the, like, where? One, this looks familiar, or two, where is this coming from? What's the energy stored in this thing that's wiggling? If it's due to a spring, it's just 1/2 kx squared. And again, the really cool thing, you'd be like, how many springs might come in daily life, whatever. Every single thing that repeats itself can be modeled as this. Every single thing that repeats itself can be modeled as this. And if you can model it like this, then you can just pretend that it's this. Do a bunch of math, figure out details about this, and whatever you figure out will apply to your original situation. It's like an analogy. If you understand the analogy, if I say that my wife is like a unicorn, I don't know. Whatever you say about a unicorn, you can then say about my wife. That's what you get for making analogies off the top of your head. So, whatever you say about an oscillator, if you say this is like an oscillator, anything that repeats itself is like this, whatever you can say about this is also true of your original situation. All analogies somewhat break down, but for the most part, a lot of the details from this you can take and transfer over. Yeah?
Does this have something to do with the harmonic series? Actually, with the analogy of like a guitar that vibrates and oscillates?
Gosh, harmonic series, I think they call it that because it flips back and forth between positive and negative, right? Oh, that's alternating series. Oh gosh, I don't remember what a harmonic series is. It's been so long since I've eaten it. I would have to check. That's a good question. One over A. Okay, I'd have to look why they call it a harmonic series. Maybe it can be modeled as a sine function. Maybe that's why.
Do you know what's called harmonic oscillator?
Harmonic means it repeats itself. No, and that's a good question. Actually, oscillator means it repeats itself. I need to look up why it's called harmonic. That's a good question. There's a reason for it, but I need to look up why. Yeah. Oh, I think yeah. No, you're good. Okay. Yeah. So anywho, those are all great questions. Words have meanings, and if you see those words in another place, there's often a reason for it. But yeah, I'll have to look into that and figure that out. Gosh, I haven't used a harmonic series in so long, which you're probably jealous of. But you'll be there too one day, unless you use them, in which case you know them really well. All right, so how much energy must the shock absorbers of a 1,200 kilogram car dissipate in order to damp a bounce that initially has a velocity of 0.8 meters per second at the equilibrium position? Assume the car returns to its original vertical position. So we have an oscillator. What's really cool is we see the word energy. And we see velocity. And so the question kind of we're going to have to write the equation for an oscillator. That may be one way to solve it, but it's not the way I'm going to recommend. I'd actually have to think through if that works. So let's just write down our givens. 1,200 kilogram car, whatever it's got as mass. We have a velocity at the equilibrium position. So that velocity is 0.8. Let's call that initial velocity. Let's call that initial velocity. Because that's what it says initial. That's kind of nice. We'll use the not because that's what I keep using with y'all. All right. There's one more given kind of hidden in here. I want to see if you all can figure it out. Give you a hint. If ever you see there's an initial, there's always a final. What's the point of writing an initial if there's not a final? Otherwise, I just call it V. Give you all a few seconds. What is the final velocity?
Is it trying to dissipate?
Yeah, the final velocity is going to be 0. Because, yeah, as the classmate mentioned, you want to dissipate it. If your shocks did not dissipate the energy, let's just logically think through conservation of energy, y'all. It would bounce, and then it'd swing back, but my energy's conserved, so I'm going to keep moving, and then it goes up and down and up and down and up and down. So unless you want your car to be oscillating forever, you need to dissipate that energy. That's the whole. You want to actually. Sometimes it's beneficial to lose energy, to transfer energy in the form of friction and things like that. Yeah, if your shocks in your car are not stiff enough, that could happen. You're just bouncing, and that's not the most enjoyable experience. Anywho, we are trying to find the energy that it must dissipate. Energy transferred. What is the word? We got a special word for the energy transferred. That the energy that is transferred. A little vocab reminder. Give you all a few seconds. What's the word for the amount of energy transferred? It's not energy. It's a special word. It's work. The definition of work is how much energy you gain or lose. That's a good way to remember work. How much energy you gain or lose transferred.
Does this have any relevance to like a collision that sticks?
There's nothing colliding here.
No.
Yeah, so we won't use momentum. I think, is that what you're thinking of? Yeah, so we're not going to use momentum because there's no collision here. Nothing is smashing into anything else. But that's a good idea.
You're gonna think like the car is like smashing into the shop.
Well, it's all one system. It's all one system because that's even, here we say, kind of like the springs have this, the whole thing has this velocity the whole time. They're coupled together. All right. If you ever see work and velocity, there's a very nice equation that relates work and velocity. Give you all some moments to think about that. What? So one of the things we learned is that the work done is the change in kinetic energy. The work done is the change in kinetic energy. Another way to think about this, you can use conservation of energy to also explain this. So this is one way this works, and literally the next thing I'm going to write is the exact same thing, just written in a different way. We can do conservation of energy. My kinetic energy initial plus the work done equals the kinetic energy final. Because those are the only energies that exist in the system. We consider the spring when it's at the equilibrium position, meaning there's no spring energy in it. At the equilibrium position, x is 0. It ends at the equilibrium position. So there's still no spring energy. And if you just rearrange this equation, oh, look at that. It's the same thing. So conservation of energy is where the work energy theorem comes from. Or vice versa, depending on your perspective. So long story short, this problem's really easy. Work equals 1/2 mv final squared minus 1/2 mv initial squared. And remember, y'all, these are scalars. The sign comes from the math. If we are losing energy, we should expect a final answer that's negative, but we don't need to assign it. It'll come out from the math if we're correct, if we set it up correctly. So work equals, well, my final velocity is 0. Oh, look, there's that negative sign we said it's going to emerge. The final velocity is 0. Yeah.
I've been having trouble, like, I do get a lot of negatives in my answers.
Sure.
Do I always just make it a positive?
Depends. You can sometimes, you can kind of logic through it. In this case, if you're losing energy, work is negative. If you're gaining energy, work is positive. So you can kind of also, if you get like a negative and you're like, I know this should be a positive, you can kind of go through it, or you just be like, I put it in the wrong spot. But in these problems, it should emerge from the math. when it comes to scalars, it should come from the math. Friction, it dissipates. I mean, where's this energy going? Friction, heat. All right, and we get negative 384. I'll let you see if you remember the unit from work. Look at all these opportunities for recall. It's the energy transferred. Again, because it was equal to the kinetic energy. So yeah, joules. Units are one of those things, you'll end up memorizing them once you do enough problems, or write them on your little note card. Speaking of which, I'll put note cards out here. If y'all want one at the end of class, feel free to come up and grab one. So, fantastic. All right, so that's just, I mean, honestly, this problem had nothing to do with, we didn't have to use anything from oscillators. Sometimes that's how it goes. But it was an oscillator. Fun facts. Fun things. Energy is useful. All right, so there's one more thing we need to mention. And then we're kind of good with this, and I'll do a recap. So, another thing that repeats... Oh, yeah, go ahead.
I'm sorry.
No, that's fine. We don't really have
So,
much.
like, how would you change the question to make it positive? Like, how would you ask it so that the answer isn't?
So if you're ever losing energy, it should be negative. If you said, how much work did it do to the environment gained energy from this heat. So I guess that'd be positive work. But if ever you're losing energy, friction, dissipation, heat, it's negative. Work is negative, yeah. Yeah.
So if you're using concentration of energy,
Mm-hmm.
and if you're like using kinetic energy, wouldn't like the final being less than the initial, like that would mean that you would have less energy, so it would be negative.
Yeah, that's exactly what the math shows. Yep, that's exactly what comes up here. You end with less energy than you started. We started with kinetic energy. We ended with no kinetic energy. Where did it go? We lost it to the dissipation. Yep, that's where the concept that ties to the math. Okay, so the next is a specific case of a oscillator, and it is a pendulum. Pendulums are classic. I mean, there's literally one out in this building. Giant pendulum there. Pendulums are classic. A swing is a pendulum. This equation that's here, so I can't derive the equation on the bottom. You don't need to know that whole second derivative, so it says equation solved by solving the following differential equation. You do not need to know that differential equation. You do not need to know this equation right here. That one, don't need to know it. But that's just a reminder, everything I teach you comes from somewhere. I can't derive this equation for you all. So we can't set it up. We also haven't taken differential equations, so we wouldn't be able to solve it anyway. But what I want to point out here is the angular frequency of a pendulum. It's really cool. It literally only depends upon how strong gravity, the acceleration due to gravity, and the length of the pendulum. It doesn't matter how big you are. It doesn't matter their mass. It doesn't matter. We're assuming no friction. The mass doesn't matter. So this means if you're on a swing set, and you and a little kid are on a swing, and you're both swinging, and we're going to assume that these things are really well greased so that there's no friction, you can, no matter how high, it also doesn't matter how high you swing. Whether one of you is swinging really high or whether one of you is swinging really low, the angular frequency is the same, assuming the lengths of those swings are the same, and assuming you're both under what you are, because you're right next to each other. The angular frequency of swinging has zero relation to how high you're swinging. It has zero relation to mass, and that comes from this equation. So it's really cool. The longer a pendulum is, the longer it takes to swing. The shorter it is, the quicker it takes to swing. And that's literally the only... So as far as if you're on Earth and you want a pendulum to swing longer, assuming no friction, you just make it longer. Oh, no, did I say back? Longer... Oh, I backwards, sorry. Make it shorter. That's period. Sorry. Go back again. If you want to make the angular frequency bigger, make it shorter. That's going to make it swing faster. If you increase the angular frequency, it swings faster. The period, the time it takes, will go down. Period is how long it takes. Angular frequency is how many radians per second. If you want, we can easily convert radians or angular frequency. If you want the equation for frequency, it's just 1 over 2 pi times the other side. So remember, y'all, this equals 2 pi f. So just divide 2 pi over. And if you want the frequency, if you want how many revolutions per, how many swings per second. But yeah, it's a really cool result. So whether or not you're swinging, like, you really, how quickly you kind of swing back and forth, doesn't matter whether you're going high or low. Assuming no friction. Assuming no air resistance. It's cool. Next time y'all like are on a swing, you can kind of test that for yourself. Yeah.
Where's the L? What's the L percent?
The O?
L.
L. Length of the pendulum. Yeah. L here is how big the string is that's connecting the thing. Yeah.
F is frequency, right?
Yes. Yes. F is frequency. Omega is angular frequency. Yes. So again, a really cool result. Remember back when I was in elementary school, when you're swinging at the same time, we use the phrase "you're in a shower." I don't know if that's a thing or not. I don't know, but what's cool is like I can swing at the same time as my daughter. She can't quite swing. If someone's pushing her on the swing, I can swing at the same rate of her, even though I weigh way more than my 2-year-old daughter does. Even if I'm swinging higher than her, we can swing at the same exact rate, assuming our swings are the same height from the grip, like the same length. If you go to a different planet, they will swing slower or faster. But on Earth, the only thing that affects how fast the swing swings is how long it is. That's it. Yeah.
There was friction with the mass pattern.
Yeah, because then the friction would be affected by the mass. Because if someone's heavier, it's going to probably, whatever that friction is caused by, it's going to push those things against each other more. So that's why the reality is it does usually affect it somewhat. But that effect is kind of small, even then. Depending on how greased the thing is. All right. So there you go. Kind of apply this equation. What is the effect on the period, the time it takes for one full swing? What's the effect on the period of a pendulum if it's double its length? And I'll be super kind and give you all the equation right here. This is the equation from the other side. I'll actually give you all the equations. Ooh, which one do we use? And honestly, if you just remember one of these, you can go between all the other ones. Frequency is 2 pi omega. Period is 1 over f. So it's really easy to derive the rest of these if you just remember those relationships. Or you can write them on your note card. Check out what I wrote. I only wrote one version of these on your all's formula sheet. So if you're like, man, I want all 3 versions, put them on your note card. The formula sheet has all the equations I'm giving you. I'm only giving you the omega one. If you want all the others, you need to derive them yourself. Or put them on your note card. All right, how are we looking? Yeah, okay, fairly reasonable. Notice that all my answers here have that capital T. That's the original period. So what's happening to the period? Is it being doubled? Is it being multiplied by square root of 2? Is it being divided by 2? Is it being divided by square root of 2? What's happening to the period? We'll go to 2 minutes. So 5, 4, 3, 2, 1. All right, so remember y'all the strat with these is you choose the equation that has the thing you care about and the thing that's changing. So the thing I care about is the period. The thing that's changing is L. So that's the equation I'm going to choose. So my original is I already wrote the original. The new one, my length doubles. I am now going to pull whatever that variable is out to the front. So I'm going to pull that square root of 2 out to the front. And then I have my original 2 pi square root of L over G. So that's the original, i.e. boom. So if I double the length, what happens to the time it takes? It goes up. How much does it go up by? Square root of 2 times your original. So if you have two swings and one is twice as long as the other one, the one that is twice as long will take square root of 2 times longer to do it. Yeah. There.
If you double the gravity, how would the math?
Oh, that's a good question. Sure. So if you doubled the gravity, we'll just do that in blue over here. So if you doubled the gravity, 2 pi times square root of L over 2g. Then we just pull that 2 out. That would be 1 over square root of 2 times all the original stuff. So if the gravity doubled, it would take less time by divided by square root of 2. Yeah.
So when you pulled, going back to, when you pulled the square root of 2 out,
Yeah.
and you to the other side, wouldn't you divide by the square root of 2?
Oh, I didn't move it to the other side. Let me clarify, because my variables here aren't clear. Let's call this T naught for original. So I'll call this T1. So, yeah, it was, so yeah, what happened here is my new period,
Equals that.
yeah, and then I rearranged it to return the original period, and then I just put that, yeah, that's a great point, yeah.
So D is when you double the gravity, right? That's the answer.
So my new period is square root of 2 times the original period.
No, I'm saying like when she asked if you double the gravity,
Oh, yeah. What about it?
that answer is
Yes, yeah. So if G doubles. There we go. So I'll leave that on there. Yeah, if I double the G, then I get that answer down there. Yep. So as gravity goes up, the period goes down. As the length goes up, the period goes up. Which kind of makes sense. If gravity's stronger, it's going to kind of get pulled back to the center quicker. If the length is longer, it's kind of actually tricky to conceptually understand why. But I guess you could say like it's got a longer path to follow it, and it doesn't. I don't know. It comes to the math. It's kind of tricky to try to think about conceptually why a longer string takes longer. I think most people that's kind of intuitive, but why exactly, I'm not sure. All right. Yeah, this is super easy. So when I said the length, it's specifically the length of the mass to wherever the pivot is. So this wording here seems really weird, but let me just draw this picture to show you that what this is saying. So how long does it take a child to swing? All right, there's a string. There's the kid. This is 0.4 meters. So this is the pivot, aka where it can actually wiggle. And the kid is 0.4 meters below that. The kid is 0.4 meters below where the swing is connected. The kid is 4 meters below where they wiggle. Yeah, 0.4 meters would be like the shortest swing ever. Wouldn't make sense. Again, it needs to make sense. 4 meters is fairly reasonable. It's a little high, I guess. It's almost from here to the ceiling potentially, but maybe to the top there. Anywho, what's given? The length. What are we solving for? The period. What equation do we have? Well, technically on the formula sheet, this is the only one you have. Omega equals square root of L over G. And then let me double check, G over L. Yep. And then you're like, oh, how do I get from that to period? And you do the derivation or you have it written down. F equals 1 over 2 pi, square root of g over L, and then period equals 1 over f. So that's going to be 2 pi. Everything gets flipped. Whatever. I'm just quickly showing you all you can derive it, or you can have it written on your note card. I don't care which.
Wait, does the L and G also get flipped?
Yeah. Yeah, so it was g over L for omega, and then it got flipped to L over g. Yep. That's why it gets flipped. So it's kind of good to show you why it got flipped between the two, and they're not the same, because it's a little subtle. All right, you all can plug in the note. It's 220, 520, whatever. You plug in L, G is 9.8, because we're assuming this kid is on Earth. Very reasonable assumption. Maybe that reasonable assumption will change 1,000 years from now, but for now, no kids on any planet but Earth. So, there you go. All right, y'all, good luck to you. This kind of finishes up oscillations Friday. I'll just do that overview. Hey, here's what you need to make certain you know for the test. Be fun. But this is it. It's everything you need to know for test 2. How exciting.
What did you say the final answer to this was?
Oh, I have no idea. I haven't plugged it in yet.